I'm Roger Grosse. I'm an associate professor in the computer science department at U of T, a Canada CIFAR AI chair, Schmidt Sciences AI 2050 senior fellow, founding member of the Vector Institute, Schwartz Reisman chair in technology and society, and a member of technical staff at Anthropic. And it's my pleasure to introduce our morning keynote speaker, Sara Hooker, who is joining us virtually today. Sara is the Vice President of Research at Cohere and the founder of Cohere for AI, a nonprofit research lab focused on advancing open and collaborative AI research. She's a leading voice in the field, known for her work on making AI models more efficient, ensuring fairness in algorithms, and addressing the broader societal impacts of AI. Sara's contributions are widely recognized. She was named one of Fortune's top AI innovators in 2023, and in 2024, she was included in Time's list of the 100 most influential people in AI. Before her current role, Sara was a research scientist at Google Brain, where she worked on model interpretability and efficiency. Sara's career bridges industry, open research, and AI ethics, giving her a unique and comprehensive perspective on the challenges and opportunities shaping AI today. We're very excited to have her with us this morning. Please join me in welcoming Sara Hooker.
Hi, everyone. I think I'm audible, but I guess someone will tell me immediately if I'm not. So yeah, it's a true pleasure, and I'm so sorry I can't be there in person. Trust me, I think the idea of your face being blown up on a massive screen is far less preferable. So I would have really enjoyed being there with you today. And thank you for the lovely introduction, Roger. I'm going to have to spend at least the next 10 minutes reducing expectations slightly because that was a very kind introduction. But I'm very excited to be here with everyone. I'm just going to share my slides. I was trying to think what it made sense to talk about with this group. And I thought, this brings together so many interdisciplinary voices. What would be an interesting topic that we could convene and might spark some fun discussion afterwards? It occurred to me that maybe one topic is just this idea of, how does science translate to policy, and how does the kind of questions at the heart of our field translate to how risk is governed, and when does it not? And what are some of the questions at the heart of our computer science field? So today I'm going to talk about what I've called, in a rather long title, the slow death of scaling and what it means for policy controlling compute. And I think this will be fun. Just to share briefly, so I lead Cohere Labs, which is a hybrid research lab. It does both open science and traditional industry. We do a lot of research. I'm just going to share this in case there's other people who are interested in these other topics we do a lot of work on. We do a lot of work on multilingual. So while I'll be talking about compute today and its interaction with policy, we have a lot of work on multilingual safety and also increasing reach for models around the world. So our models cover 101 languages. And sometimes you realize once you start trying to list 101 how difficult it is after the first 20. And I'll just briefly say this here. We also do research grant programs. So I know many people are across different disciplinary fields, so happy to talk about that if it's interesting afterwards. And then, of course, maybe what will be more relevant to today, I'm going to talk about some of our policy work, which is about bringing technical perspectives into governance. So how can we make sure that we bring scientific evidence to kind of inform some of these discussions? And today I'll talk about compute. Actually, yesterday we released a primer about multilingual language and safety gap if people are interested. But today, what is fun for us to talk about? So I work on designing and building large-scale language models that are efficient, multilingual, reliable, and trustworthy. And today I'm going to be giving a talk about a a paper I released last year with actually a very boring title. And the title was On the Limitations of Compute Thresholds as a Governance Strategy. But I'm going to argue and kind of pose to you that this actually grapples with topics at the center of machine learning progress. And what this paper asks, and what is very important for our discussion, is that what it's really asking is bigger always better? Um, are we trending towards like a world in which we're constantly scaling? And the implications for policy are, can you predict at what points risk emerge? And this is important because as computer scientists, it's shaped the ecosystem our research sits in. We have swag now that says GPU poor. Michael Jordan, the computer scientist, not the basketball player, said, "Today we can't think without holding a piece of metal." It has changed the very fabric of who contributes. So it's resulted in a major shift of contributions from academia to industry research. It's also meant that many labs publish far less because the amount of compute needed to participate means that there's much more anxiety about all that capital being just released in terms of sharing insights. Um, I'm very proud that Cohere Labs is one of the few labs that still publishes frequently. But also, compute has determined who gets to participate and who doesn't. So this is a plot which shows really the number of what is estimated to be significant machine learning systems from Stanford. And it shows that really measuring this from 2002 to 2022, a whole continent is blank. And you see this concentration of who gets to participate to be in a few places in the world. It also matters for policymakers, this question of whether is bigger always better, because compute thresholds, which were policy about when a model becomes more risky, were widely adopted in the first AI governance policies. So the first White House executive order in the last term on AI, as well as the European EU AI Act, which was passed. And it's this idea that models trained above a certain threshold of compute should be subject to more scrutiny, that it equates with more risk. And this was formalized as anything above a certain amount of flops. It also matters because it's often implicit in the responsible AI policies put forward by frontier AI companies. So Anthropic's this responsible policy is called responsible scaling. Implicit is the idea that scaling is inevitable, and the only caveat is how we do it responsibly. And many frontier labs have adapted responsible scaling policies. In fact, the Frontier Safety Framework, the invitation for policies, put this front and center as like one of the things to consider. What are the thresholds where you get more risk? And one of them, central to the discussion, has been this idea that scale is a primary ingredient. It also is really interesting because it's also informed national policy. Acquiring compute is now a national priority. It's in fact being motivated by how do we secure and make sure that governments have a say in how their researchers get to participate. We see this with AI Singapore, with India, but it's much more far-reaching, and it's this idea that unless you have compute, you cannot play in the AI innovation space. And it's also very true that this is informed policy like export controls, which are really based on this idea that we have to control who we sell GPUs to, because compute is national competitive advantage. And so I've convinced you that this is actually an important question to ask. Like if all these policy focus, as well as all the focus of how frontier AI companies self-govern themselves is based on this premise of scaling, well, then maybe we should ask, is scaling really inevitable? And are these policies really sensible? Is bigger better? And should compute be the foundation of governing risk for generative AI? And so I think this will be fun. I'm going to actually very much try and stick to the 40 minutes because I think we will have some very engaging discussion afterwards. And please, as you go, I think I guess this format doesn't allow for the normal back and forth, but I would really welcome. I think it will be nice to have a much more engaging discussion at the end. And so the first question we have to ask, if we're going to ask this question of like, is scaling inevitable, is what has been the role to date of scale and data? And arguably, it's been the central ingredient. So we've seen a bigger is better race in the number of compute parameters. And this has characterized all modalities, both vision and NLP. It's also involved large increases in both model and data set size. And we just see this massive increase of both the volume of data and in the parameter count of our models over time. It's been captured by Rich Sutton as a bitter lesson. And he says very well, the only thing that matters in the long run is the leveraging of compute. And this is kind of a punch to every computer scientist ego out there, because what's being implied is that nothing in computer science has worked as well as pairing a model that can learn patterns for itself with scaling. And so today, to kick us off, I'll posit, is Sutton right? Is this, are we just kind of participating in the bitter lesson? And is the primary ingredient to progress scalability? Now, normally here I would poke you all to answer, so you're lucky. But I think that there's an argument that is clearly in favor of Sutton, right? Which is that the charts I just showed you of increasing model size and data set seem to suggest he is right. We've also just observed that, different capacity regimes seem to allow for different emergent properties. And it is a very simple formula, which is what makes it so persuasive. Just throw more parameters at the model. For example, we do see that instruction tuning improves zero-shot performance, but only above a certain size. And this means zero-shot performance just means that you can prompt the model on something that you consider an unseen task that you don't think the model's seen before. We can get into a debate about whether that's actually feasible or not, given how much data is seen in pre-training. But the premise is this improves the model's ability to generalize on what's unknown. It also seems to depend on having a larger and larger model to take advantage of this. And certainly, if you looked at something like Chatbot Arena, it's very clear that the largest models index far higher, right? So even the smallest open model with a disclosed parameter count is DeepSeek, which has 685 billion parameters. So DeepSeek became known as really having really being efficient, and but it's very large, so it has an enormous amount of parameters, and this is why plausibly throwing compute is a problem at a problem still widely favored, because empirically it seems to work and it's more de-risked than the more difficult problem. We have to invent a new optimization technique, or we have to really reinvent the algorithm. But also, and this is interesting, it tends to fit very well into industry quarterly planning cycles. So it's hard to deviate from throwing more compute if throwing more compute on average tends to work well, and it fits into a 3-month kind of cycle of trying something new. However, and this is where I'm going to have fun and introduce some counterpoints, is that a key limitation of blindly following this bitter lesson is that the relationship between weights and generalization is still poorly understood. And one data point for this is that even models at the same capacity, the same size, has become far more performant over time. This is looking at models that are under 13 billion on the LLM leaderboard over time. And you can see that these are all small models that have been gained much, much higher performance. But also, smaller models frequently outperform far larger models. So this is the best performing small model over time, but it's also all the large models above 13 billion that are outperformed by that small best performing model. And so we see over time, more and more larger models fail to compete with smaller models. We also see this in our own work. So we do a lot of work on multilingual. iExpanse 32B is a state of art, and it outperforms much larger models on multilingual. And this is on a private leaderboard. I'm a big fan in private held out test sets. And it includes like Claude, Mistral Large 2, Llama, and I think this is part of it, which is that you can outperform, especially if you're aiming for a particular use case. Like our focus is multilingual performance. We also recently observed this with multimodal, where we can outperform 90 billion parameter models, 72 billion parameter models with 8B, which is really impressive because it's 11 times, it's often outperforming models 11 times its size. And so I would argue that, in fact, we observe a highly uncertain relationship between compute and performance. And I'll share some reasons why. One is that we observe diminishing returns to adding parameters. So we need millions of parameters to eke out additional gains, and now we need billions. So this is an old school example. It's from the computer vision days, and it shows from inception V3 to V4. If anyone in this room knows inception generations, that's fun. It's a mere 10 years ago, but it feels like a lifetime away. And what we show is that if you double this, you get a measly 2 percentage points. So you've doubled the size of your model and you're just squeezing out performance. But we also see this with our current paradigm, right? So we have all these bombastic headlines about the end of scaling. And I think arguably I'm not saying it's the end of scaling, but I am saying there's diminishing returns as you increase the amount of size. We also know that there's redundancies between weights. So you can use a small held out percentage of weights to predict the majority of weights in your network. What this is really saying is that all these are very correlated. So you're learning a representation where many weights are correlated. And frankly, one of the most persuasive data points, I've done a lot of work on sparsity, where you remove weights from the network and you kind of prune the network, similar to how the neurons in our brain are pruned, where a lot of our how we develop our brain is by introducing sparsity, where unimportant neurons are pruned away and certain neurons are strengthened in connection. But we see the same, we're able to prune networks. And what we find is fascinating because after you finish training, you can remove the large majority of network weights, even if you do it at random, the most crude possible way to remove. But you can only do it at the end, which means that while it seems to be important for models to be big while you're training, so we condition a very good optimization space, afterwards we can throw it out. So it says more about our lack of good optimization techniques than it does for the need for these models to be so big. And to be honest, a lot of this is because we optimize for average error. And when you optimize for average error, what you mean is you're optimizing for like the most common feature at any one time in a batch. And we see this in a few ways. It takes a lot more capacity to learn rare features. The majority of features are learned early in training. And the majority of common features can be learned by smaller models. All this says it's taking us, we're spending a lot of compute resources to learn a small part of the distribution. A lot of my work over the last 5 years or so has been, what do we gain when we vary model size? What is lost? And we find that when you remove weights, like what you lose is the long tail, and you lose the rare examples. And it's worth emphasizing this finding because what it actually implies is that we are using the majority of weights to learn this tiny part of the real world distribution. And it's very inefficient, which means even if we scale, it's kind of like building a ladder to the moon. We're going to keep on paying a huge penalty for learning these rare examples. I included some of these from some of those earlier works, and you can see something like this, ImageNet test set, what's the true label? And this is actually a toilet seat. So this example is scale dependent. This is what a normal example looks like. And we have this, what is the true label here? This is espresso. And here, maize. Here, plastic bag. And so what you're gathering is that all these examples are very challenging, but that's what we're paying for when we scale a model. It's learning this part of the distribution. And sometimes these are simply incorrect or simply implausible. So we're spending a lot of also capacity learning noise. Then we see something like the cloak. But the final, kind of part of this that I'll talk about is that we also find part of why we don't have a good understanding of the relationship between scaling and generalization is that data quality can compensate for a lot of this compute. So we can get away with much smaller models if we care more about the data distribution. And this is coming to the fore now when we think about shaping our data space, making it malleable. In some ways, we're just trying to get away from the shortcomings of our networks being optimized for the average, right? If you're optimizing for the most common features, one way to address it is to reshape the data itself so it more represents the distribution you care about. But the final counterpoint I'll say is that really this belief that scaling is inevitable, it doesn't capture the algorithmic breakthroughs that have fundamentally changed our field over the last 5 years. We have seen a profound shift. Most of computer science has been around the idea of a model, like you're building a model. One of the first networks on the connectionist side was the perceptron. It was always centered on the algorithm. But now we're able to both optimize in the test time setting, so no gradient updates allowed, but we can do a lot around the model, and we're able to optimize the data space. And that's pretty profound because our optimization space is a lot larger. And we also see that this has completely changed the kind of economics of where you place compute. So if we previously were in this very compute heavy regime, training larger models, training longer, increasing data set size. I would argue we have these incredibly compute light techniques, like we have chain of thought, we have distillation of synthetic data, reasoning, increasing context length. And then we have what I call gradient free techniques. These are completely free in terms of no updates to weights. And you can have things like model routing, agents enabled with tool use, and best event sampling. And that profoundly changes the rate of return for compute. Because if we're able to get these massive gains without spending that much compute, then we're in this new regime where that relationship or our ability to predict the return from scale is completely changed. So where are we and why does this matter? And what does it mean for how we think about risk? Compute thresholds, when they were proposed, were set as a hard-coded threshold. And this means that experts had to estimate the correct number to set it at. This was done in a very interesting way. So the White House executive order went first, and it set it at a certain level, and then the EU set it at a slightly higher level, but both were set at kind of similar, so 10 to the 26 floating point operations. But it was an estimate, and it was a hard-coded estimate. So any models below that amount weren't analyzed for additional scrutiny. Any models above were automatically kind of routed for additional scrutiny. They will also unusually assign a precautionary policy, which is typically being reserved for certain types of policy, like climate change, where you have to estimate and you have to guess what future harms will be. And precautionary policy is tricky because it involves premising a policy upon an estimate of the future, which typically humans are notoriously poor at. And what this meant is it put pressure on policymakers. They had to estimate where would the scaling go and what would happen. And in retrospect, and this was a mere, year or so ago that the EU AI Act was passed, it's been, I think, in many ways, the landscape that they predicted has fundamentally changed. And I will say, historically, successful thresholds are sensible when they're applied to well-behaved distributions. So that's things like our physical features, which tend to be very well-behaved because we're governed by the physics of being born. We have to, in order for us to survive, we have to fit into a normal distribution typically for things like blood pressure, chest circumference, resting heart rate, baby way. These are in many ways dictated by the gravity and physics of the world we live in. And here you often see that setting a threshold works well because this distribution is very well behaved. That's why we see this work well in things like medical fields. So for example, many hospitals have hard-coded thresholds for when an infant is considered underweight or premature. There's also drink driving limits around the world that are hard-coded, in part because there's just a physical limit to how we can tolerate different types of drugs and things like that. The same is true for overweight, which typically is hard-coded. However, model capacity is the furthest thing from a normally behaved distribution, so it's rapidly changing. And this is part of what has been really difficult about that setting of the hard code threshold, because two trends have happened simultaneously over the last few years. One is that while compute has driven progress, we simultaneously see the bending of scaling laws, where smaller models are becoming much more performant and riskier. And so much more riskier models now fall below the threshold that was set. Simultaneously, we see that more and more models have just blasted through the threshold set by the EU AI Act. So at the frontier, and particularly as we go into mixed modality training, we're going to see some models kind of pushing out that compute threshold. But the ones that have passed, it's really interesting because they're often not as differentiated from previous generations. And so there's this really interesting question. If you have a small model empowered with tool use, is it riskier than a large model that's not enabled with tool use? And these are the questions that policymakers are going to have to grapple with. We also, I think the other dilemma is different modalities have drastically different levels of compute. So for example, it's really interesting, but typically, so something like biology and coding require less compute. So we tend to think of coding as a very complex task, but actually as a language, typically it's far less complex than a spoken language that is developed over a long period of time. Our code is limited by both the hardware and the need for adoption, and computer science is not that old. You know, we started modern computer science in 1957. So you can actually have a very good code model that's far less parameter count. And then biology is also, you know, in terms of the tasks that are used, typically the data is more confined. Only a few combinations co-occur. And so we need less compute. But that means that a single threshold is unlikely to do well for all. And the truth is, the reality is that compute is changing as fast as the technology it serves. And so these are the distributions where it's most difficult. So one option is you can tailor thresholds to each domain. So one thing that was done already was biological models have a different threshold. However, this has already been eclipsed by multiple models. And also, it introduces a possibility of hacking, right? So if you define a biological model as 50% of the data, you could have people just train for slightly less than 50% and call it a non-biological model. But there are also large gaps, and I just want to do a time check because I want to leave plenty of time for questions. How are we doing? Could someone message me? Maybe, okay. Oh, excellent. Oh, so we have 10 to 15 minutes until questions. Sorry, Daniel's messaging me. 10 minutes until questions or 10 minutes to the end of the slot? I want to make sure we have enough. Okay, yes. Okay, great. So then I'm going to go a bit quicker because I want to leave plenty of time. And I think there's some other limitations to FLOP, which I've listed here. But I think one of the biggest ones I mentioned, which is that we now have a lot more compute applied post-training. How do you account for that and how do you trace it? And you have a lot of gradient-free methods that don't even require the FLOPs. And so how do you specify how that increases risk? So I want to end with this, and then I want to open up for, leave us plenty of time for discussion. It's hard to predict, especially the future. AI policy should be informed by scientific evidence and be transparent about what risks are of interest. I think what's remarkable about the compute thresholds that were chosen in the policy last year is that there was no formal justification for how the numbers were arrived at. And this erodes accountability. And it also means that in retrospect, it's very hard for us to understand how we got here or why it doesn't match the current landscape that exists in terms of how computers actually used. And I think that, after this paper that was released last year, there has been more nuance around compute thresholds, and there's been more discussion about the limitations. However, we now see the same simplified motivation being applied to chip controls. So how acts that are, restricting export of chips. And so I really think there has to be more forums which are interdisciplinary and which connect both computer scientists as well as policymakers and civil society, to understand, well, what is how do you equip policymakers to form policy that is sustainable and lasts more than 2 years. And this is important for multiple reasons. But I think more than anything, we should be humble about our ability to model the future. Warren Buffett once said, "Don't ask a barber if you need a haircut." And in the same way, don't ask a computer scientist if we can model the future or scaling laws, because our temptation to say yes may override a necessary humility about the limit of our current tools. Scaling laws are certainly useful when you're predicting your next training run. So you know what hardware you're using, you know what data, you know what architecture, but predicting out months and years and trying to use that to inform policymakers, I think one of the most unfortunate mistranslations has been an understanding that these hold and that these can be used as reliable predictions. And so I think this is also very important in terms of how we frame this discourse and our role as responsible stewards for grounding the expectations around how we can predict. But I'm going to open up there. I would love to invite questions or discussions or even perspectives from the room.
Okay, thank you, Sarah. I'll maybe start things off. So I think it's a very intriguing claim. You have a lot of evidence for it that maybe scaling isn't that useful. But then we also heard a lot of impressive statistics in the earlier session about the investments in data centers. And so the 1% of GDP and things like that. So are these companies making multi-billion-dollar mistakes in investing in data centers? Should they stop doing that?
Yeah, I think that's a very fun question. So I think for one, a lot of compute is actually in serving. So there's this presentation has very much centered on the scaling of the optimization process. But the reality is, and I do a lot of work on efficiency, the bulk of compute is how you serve the model, because especially as you serve billions of people around the world, that's where even a very efficient model, you get massive compute workloads. And so certainly I think investing in compute is still very important because AI is now becoming part of many people's lives all over the world. Do I think that training runs or optimization will require massive data centers? Certainly at the frontier, when you do new combinations, typically our solution when we don't know what to do is to throw compute at the problem. I think my argument is not about that. And in fact, we see continued new generations of models to be throwing a lot of compute at the problem. However, I think my argument is that that is ultimately, especially within our current paradigm of architecture, unsustainable. And so we're going to see ever diminishing returns. And the reality is we now see much more interesting within the established domains that we know more. We see bending of compute very frequently, and so much smaller models that are more performant than their larger counterparts. And so there can be these dual trends, and that the reality is that that's what makes a simplified kind of narrative of scaling unfortunate, is that it doesn't capture that most efforts are about really bending, and there's marginal gains within our current architecture paradigm of continuing to scale. Yeah,
Hey,
that was a fun one to kick off.
We'll now take questions from the audience. Because the microphone won't pick up the audience questions, I'm going to repeat the question so that Sarah can hear it.
So it might just be a form of petulance that makes me not like the scaling law because it seems to be a fact of reality. However, we heard earlier that if the risk proposition isn't worth it, then you wouldn't do it, and we see how the scaling law is going to lead to various environmental damage, not even as a risk, but quite likely if you spend that energy. So in that context, I'm just wondering, what's the other scaling law? What's the less damaging scaling law which impacts the technology with benefit in terms of its performance or whatever other factor or applicability, but provides some sort of benefit like that, even if it wasn't quite as fantastic as the other one? But what's that other scaling law that's going to bring us forward that is an alternative to this sort of environmentally and otherwise disastrous type of fact of the technology it was seeing?
Yeah, I mean, so I think that's, I think firstly, I'm glad environmental impact came up in this talk. I do a lot of work on efficiency, and I partly it is very much motivated by both access and also understanding, especially as our models are used by people all over the world. How do we make sure that we're reducing that impact? So there's two ideas. So I think your question is pretty much okay. So if scaling is not the way, how do we keep on improving these models? Or like, what are interesting ideas in this way? One is the biggest ceiling typically on scaling is the model architecture. So the biggest shifts we've seen in scaling dynamics are like what model architecture plays well with hardware and software. There's another paper that I wrote, which is the hardware lottery, which is very much about this. Like you win the lottery if you find a hardware architecture that works for given hardware. The reason why scaling laws I frankly think should never be used as a prediction technique in a policy setting is that it would have been impossible to predict transformers using scaling laws based on convolutional neural networks, the same way it would have been impossible to predict scaling laws for convolutional networks based on what came before that. So if a new architecture comes along that profoundly changes it, that's probably the biggest lever because it changes your entire slope of the rate of return. And it's the rate of return that matters. It's not just saying you want scaling, it's what's the rate of return for that scaling. So let's take architecture out since there's not very promising ones on the horizon. I think a lot of smart people are working on it. What else can happen? I actually am quite excited because I think we're in a very exciting time for optimization. But for the first time, our data sets are not fixed, right? We have cheap synthetic data that we can use to try and shape the data that we have when we're trying to model a problem. Why is this profound? Because for a long time, we just accepted the data that we had, and then our model had to do all these acrobatics around the data. But now we can try and really increase efficiency by shaping the data space, by caring more about certain parts of the distribution. For example, I work on multilingual, on rare languages. For me, this is profound because if I can shape the data and create data that better represents languages I care about, I can really help represent that language when it gets to optimization stage. And then the other thing I'll talk about, the second trend I mentioned in the talk is now we're doing a lot more that is gradient free, which means we don't even update the weights. Like if you think about something like a tooling in PowerQual, the model isn't, that's got nothing to do with training updates, but dramatically increases performance of the model. If you think about something which is like adding RAG, you have retrieval and you're just adding a database, but you're not really fundamentally, you're doing very light actual adjustments to the model. So this is very promising because this is cheap, increases performance dramatically. However, it does mean that all this policy being based on compute thresholds becomes somewhat strained because all these things are very cheap and so they don't really impact flops. Yeah, hopefully that answers, but yeah, very good question.
In the front.
Thank you very much. Great talk. Two of my favorite researchers are here today. I'm very happy to be here. So you mentioned gradient-free teams for developing these models that we now have access to. Do you think it's finally the time to go even lower level and utilize other frameworks like evolution-based methods?
I didn't hear the last part, but I did hear utilize RL frameworks. Yeah, maybe the last bit could be repeated for
Sorry,
RL frameworks
other
for.
frameworks for optimization at lower
Oh,
level
yeah.
and evolution-based genetic algorithm, etc.
Yeah, I do think so. Typically, one of the things that's quite fun about where we are is that the most successful optimization, it's been very hard to deviate from what has worked optimization wise. Gradient updates tend to be very persuasive as a, as a learning methodology. That being said, I do think the fact that we have such representative language models opens up the idea for much more modular interactions, which maybe you don't have a jointly trained model, but you route requests between models. Or maybe an agent can interact with another agent and there's no gradient update shared, but there's enough information parsed that you still successfully achieve your objective. And why is that really interesting is that it just opens up this world in which we're not just doing optimization within the gradient update lens. Your point is about RL. I think there's also a lot of questions about RL. So RL, when it was applied to natural language, is quite interesting because natural language is a very predictable space by the time you've trained a model. So by the time you trained a model, it's not as expensive a search space as it might seem. Even though you can choose from often trillions of tokens, in practice, once I say I live in, there's only a million or 10 million combinations of what the next word can be. And that means that RL worked very well in language settings because RL is typically two parts, right? You have to, when you're doing reinforcement learning, you have to first understand, you have to both search a space as well as calibrate a reward. So, like, was the action I took good? And then what action do I take next? And when it's well conditioned, then your search space is pretty narrow. The most enormous challenge that confronts us now is that we are back in a true RL setting. Like, we want to do multi-step optimization. We want agents to take actions and then pass it on to other agents. And that's where RL has typically confronted all the issues we have in just four fundamental machine learning problems, which is our inability to estimate certainty. We don't know when we're wrong. Also, our inability to control for cumulative error. So typically we can have some margin of error in a single prediction, but if we pass it on, it kind of accumulates over time and deviates you from the course. So I think these are fascinating. I think they're present in very simple problems in machine learning. Like Roger kindly is introducing me today. His courses have many of these same questions in a very simplified, fundamental theoretical form. But now we're facing them with these massive systems. So all to say, all bets are off, but I think we're truly back in the original holy grail of RL, which is that we have to somehow make these models work over multiple time steps in complex environments with large search spaces. And so I think we're going to confront again the brittleness of our methods to some degree, and it will be fun because it will push us forward as a field. We'll get much better at these uncertain environments.
Thank you very much. I think it's definitely very good to have more nuanced conversations, right? And I think twice and three times, I think, in your presentation, you talked about having scientific consensus to inform policy around this massive drive and race and distribution where compute is. And there's a lot of things that's tied to this, for sure. Can you say a bit more? Because it seems like a lot of what you're saying, the type of model that is being displayed, are these frontier models, except for the ones that you're also trying to showcase as well, right? Saying like, oh, this race is really between the very giant players. But there are other ways of doing this. Then the next question is, there is a question about this distribution of compute, right? The actual hardware allocation, where this infrastructure is at. Can you say a bit more about and I look forward to reading your policy papers as well. What would you recommend in terms of, hey, majority, I would imagine maybe only 10% of the labs are really driving the demand for compute. And then most of other labs and most users of this are just one-off. They're just testing it, playing with this, and using some compute. So in a sense of like, are we talking, who are we talking about who are actually driving this type of race for compute, but also how can we widen that net to bring more people in? So it's a policy.
Yeah.
Can you ask this question?
Yeah, that's it.
Yeah, okay. Maybe I'll tackle the second one because I think the first one I wasn't quite sure where the question was or if it was a statement. But the second one, I think there's two different scenarios. There's the compute needed for innovation, and then there's the compute needed for deployment or for access to these models, right? So for innovation, what's very clear is there's two aspects to this. One is a massive disparity between access for academics and also access at industry labs. So if we talk about, the first use case, which is innovation, progress, let's say we're even bending scaling laws. Let's say we're still, we recently released a multimodal IA model, which expands coverage for multilingual languages, is the best open weights multimodal model for these languages. It's an 8B model. We did that intentionally for access. We still spent a lot of compute training it because there's many steps that goes in along the way, and you have to innovate and you have to do ablations and things like that. So your final model is efficient, but it's still, you have to have a lot of compute. There's a reality that we need to do better in governance systems to make sure that some of these compute access are also available to academics. We have a grant access program for compute. Other frontier AI labs also try and bridge the compute gap in different ways. So that's certainly true. I think, the comments about whether scaling and the final performance of the model are true are independent from the fact that to even develop a small model, you still need a lot of compute because you have to try all the combinations along the way. In parallel, though, there's the second use case, which is deploying these models. There, the compute requirements are enormous and only going to grow because those are about like how we serve models to millions and billions of people around the world. And even if the individual model is very small and getting smaller and we're moving away from scaling, we're still serving more and more people every day. And so it's kind of like if you have a product which is wrapped in plastic, if you make improvements to that product that require less plastic, that improves reduces the footprint. But if then you sell it to 1 million or 1 billion more people, you still are releasing a lot more plastic. And that's where we really have to tackle and make sure that the footprint of these models is so efficient and so optimized by the time it gets to deployment. But we also have to have a serious conversation in society about how do we account for these data centers? Where is this compute coming from? And this is, again, at the intersection of society, policy, and our technical expertise. So there are actually two different use cases. The second one is actually much bigger. I think people often misunderstand this, that the compute required for training is just a fraction of the compute required for serving a model. And that's why when Raja asked, should frontier AI companies invest in data centers? Almost certainly, because the need and the use of AI is going to become ever more prevalent. Does that mean that we also simultaneously have to have a conversation about how we reduce that footprint as much as possible and how we make sure that there's access for innovation? Yes, that's also true. Yeah, hopefully that's helpful.
Hi, thank you for your talk. I have two questions.
Oh, excellent. Nice.
one question?
Just one? Do you think it would be better to maybe take a more social science approach to regulation in terms of, do you think it might be better to regulate models based on emergent capability? Like have a bunch of tests, like can it answer this question correctly or these sets of questions correctly? Or compare it to the current state of the art, or like some baseline model that we know it has like a particular set of capabilities, and say, if it can do that, we need to pay attention to it.
Yeah. Okay. So I think this is fun because I actually didn't talk about this. So I wrote a grumpy paper about thresholds, but I actually did propose some things I thought, because I tend to think it's not good to not be an actionable grumpy person. So I actually wrote some recommendations at the end of the paper. One of which is that yes, almost certainly. I think compute can be used as one ingredient, but it cannot be used as the only ingredient for assessing risk for all the reasons I mentioned, where the threshold is already, dare I say, irrelevant a year or so after all these thresholds were passed. But then secondly, what you actually, and I think this is the second component, is I don't think you actually care much about hard-coded thresholds because I don't think we're very good at predicting the future. And I can be swayed otherwise. I know that we're quite attached to the notion that we are good at predictions, but I think history tells us it's very difficult to predict what will happen, even in the scenario you're talking about, which is like, oh, it shows this capability. I think it's much more important the relative distribution of ability. And if I were to guide policymakers, what you care about is dynamic relative percentiles. And what that means is that at any one time, policymakers' time is limited and they want to apply more scrutiny to what's at the edge of capabilities. And that's why percentile based makes a lot more sense. Like, let's understand for a few key markers of ability that we care about, what's in the 90th percentile. And that can look like a few things. I want to actually add a few comments there to what you mentioned, like can I answer this question correctly or not? My big recommendation for policymakers is that there has to be an investment in private test sets. The reason why is that we have seen, and it's very clear. I just released another a work. My lab released a work that I'm quite proud of, where we even showed this is true for like the chatbot arena. There's an over optimization of popular benchmarks and reward hacking. And so if policymakers show, oh, we care about biorisk and we care about these things, it's very easy for someone who builds a model to then optimize so the model doesn't do those things. So that's the third ingredient. One, care for a basket of metrics, not just compute. The second is treat it as a dynamic percentile-based threshold, not hard-coded. Because why do that to yourself? Why be proven wrong a year later? It's unfortunate how quickly you can that can change. And then third is really keep it private. You should have, policymakers should create and curate data sets. I think that's also true for language reporting and safety across languages, for future risks. There should be benchmarks which are not released that can help policymakers guide where are we in this percentile. Yeah, hopefully that's helpful. I think it's a very good question.
Hi, thank you for the talk. My question is, to what extent do you think that memory needs to be improved to overcome the potential limitations with scaling that you describe? Are larger context windows sufficient, or do we need to create new memory architectures for these systems to improve their functionalities past increases in scaling?
Yeah, that's really fun. So why is memory fun? I think that's worthwhile first posing. Memory is really interesting to think about because in many ways our models are these kind of really awkward learners where they're trained on the distribution that they had access to, and then they immediately become stale. And so a lot of the way that we've thought about memory is how do you store information that's more dynamic and how do you add information over time? context windows and retrieval, databases have become one way to do this. I think that there's some things that I think are still a little bit crude here. So one is that both retrieval systems as well as context don't introduce what is core about our memory as humans, which is saliency. Saliency is one of the most important traits that we learn. So what to pay attention to and what has relevancy. And none of these current techniques, including, by the way, global gradient updates, have saliency, right? There's some degree because you have like your more common features, those end up being over-indexed in gradient updates, but there's not the same notion that we have, which is we have long-term memory or short-term memory. These are, these are associated with different parts of our brain. And I think that is one of the most fundamental properties we will have to tackle as we want to meaningfully create memory stores. But it is an important question. And for me, context windows are probably the least interesting solution, although I understand why they're attractive. It's a very nice way for us to quickly get gains in personalization and quickly get gains in some of the problems that we want, but it doesn't really tackle the long-term problem of saliency or what to weight more heavily. So that's the fun part for me. If you were asked me, like, what would be interesting to work on for, the next few years and really throw yourself at.
Hi, Sarah. Sorry, that was kind of loud. I'm Steve, and I work for Imagine Canada. I have kind of a high-level question. How does Cohere approach hiring AI academics and ensuring they're continuing to work on things that advance humanity and not just commercial interests? And do you have any concerns about how other big tech companies are approaching this?
So maybe I'll just talk about Cohere Labs. So I think that in many ways, this is, maybe I'll talk about, to take a step back. Why is this question being asked? I think this question is being asked because in some ways the role of industry labs has changed recently. Research within industry has always had, to some degree, a question mark, right? The spaces for research have traditionally been in academia, and before that, patronage from like wealthy individuals, the gentleman scientist. I find this question of like, what are the spaces in which breakthroughs can happen very fascinating. I'm happy to give a whole talk about that a different time. But now it happens in industry, a lot of the most, the work at the cutting edge. How is that relationship and has it evolved? Well, when we first had industry labs, when Google started Brain, when Meta started FAIR, Apple, Microsoft research has been around for decades. But when these other spaces did these dedicated bets on AI that were industry, the talent had a lot of say because there were so few people who had been working on deep neural networks. Canada being the epicenter, right? So like when I was at Google Brain, all of my directors and everyone who was there was from Canada because those were the people who were working on deep neural networks. And that meant that there was a lot of say about how research was done because there was a narrow group of people who could do it. There's still a narrow group of people who can do frontier research. But I think what has changed is, firstly, there's differing opinions about the safety of publishing the way that we used to, right? There's concerns that maybe some of this technology is too dangerous to release in the same way. I think that's a worthwhile discussion to have. We've chosen to publish, but I admit when we release open weights, part of me is candidly worried about misuse. I think about it a lot. Like, how can we have protocols that allow for open weights and access, but also allow tracing of misuse? Because our research is not just used in conferences anymore; it's used around the world. I think there's also a probably less honorable reason that, some people just, worry that a lot of money is being invested. And do we share all of our insights? I'm quite proud that Cohere has, and our lab has continued to share like a lot of the insights that drive our work. I think that's the right decision. Removing for a second the safety consideration, which I do agree should inform how you share and, the protocols that you have in place. There's another question that was kind of within, does it inform what you choose to work on? When I joined Cohere to start Cohere Labs, we decided to work on this problem of 101 languages. And at the time, cared. I'll be honest. No one cared. I think, all the models were focused on English and Chinese. And I think most people said, oh, that's so great you're doing that, which I'll share with you all here. Typically what that means is between the lines, oh, it's great you're doing that. Go for it. But we're going to work on the important problems. And then we delivered Aya and it was state of art. And I think it sparked this really important shift in people realizing, hey, this is about, serving people all over the world. And I think it's very catalyzed a movement towards multilingual. That being said, like when you work on 101 languages, everything, all the techniques that get you to 101, it's just nuts. When you trickle them down to a smaller group, they're even more powerful because it's so difficult, so many different distributions and so many core problems there. So I think that for us, it's always been, we're a research lab, we're working on the next problems. But I will say, never has research and immediate impact been so close together. When we release an Aya model, it's immediately used the next day by people all over the world. And that's something different for our field. So I highlighted a few things there. Some of them are a bit different in the concepts. But I think to put it succinctly, we are now in a different place in terms of where innovation is happening. It's not just in academia. And often, the very shape of it is changing within industry, where there's less publishing or sharing outwards than it used to be. Does that mean that it cannot exist? No, I hope Cohere Labs is an example of us crafting a third way. We're a hybrid lab. We care a lot. We release open weights. We share papers. But I do think it means that we have to have this conversation as a community, and also have to have better incentives in place within universities with enough compute that academia can have a real voice in this and not be confined to the realms of like, oh, you do the evaluations and the industry labs will do the models. I hope that gives at least a few touch points. And it shares a little bit of what I think about as we think about our research agenda.
Okay, thank you. I think that's about all we have time for. So thanks, Sarah, again for the interesting talk.